Hello, and welcome to AWS reInvent and to this session, which is building BMW Group's customer engagement platform on AWS. So who likes cars here? Yeah, we all love cars, right? So we're going to learn about how to configure cars and how to do so using microservices. So great mixture of topics. So what are you going to get out of these sessions? We will start with a quick introduction into microservices. Then we'll dive deep into a real-world customer experience from my customer, BMW. And we'll close this off with some guidelines and resources for your own microservices projects. My name is Konstantin Gonzalez. I'm a principal solutions architect with Amazon in Germany. And this is Patrick Lanners and Julian Rödig from BMW. And I'm very happy to have my own customer here on stage sharing their experience here. So let's start with monoliths, which are the opposite of microservices, if you will. And this is how applications have been developed for decades, right? Big, large application. Monoliths tend to be rigid, hard to change. They tend to be hard to scale as a result of rigidness. They're also pretty hard to deploy. And people tend to feel locked in once they reach a technical decision for their monolithic application. It's hard to change it, and so they feel locked into those individual choices. And they are hard to reuse because every monolith is like a big, wonderful snowflake, but really hard to tear apart and repurpose elsewhere. And they are also easy to break because if one piece in the monolith doesn't really work, or if it breaks, it takes the rest of the monolith with it, and that's really hard to fix. So the key thing here is to understand the monolithic development lifecycle. You start with a lot of developers contributing code to the code base, building a single app, and then you have like this single, wonderful but big and complex build, test, release cycle, which is really hard to do, and it typically involves things like working over weekends or late night, a lot of head scratching and hoping, and at the end of the day, you don't do that very often. So customers I talk to, they tend to deploy monoliths a couple times a year, and after that it becomes stressful. By contrast, microservices. So microservices are composed out of many, many small and autonomous services. So the key thing here is autonomous, and each service is specialized to do one thing and one thing only. And as a result, microservices projects tend to be a lot more agile. They are very flexible to scale because now you can scale individual microservices each on its own. They're easy to deploy because much smaller, right? And this gives developers a lot more freedom because now you can have like many different technology decisions, one for each microservice individual stack. And if you want to change the technology in an individual microservice, it's easier to do because the scope is much smaller. And finally, they are very easy to reuse. You can copy-paste the whole microservice and use that as a template for a new microservice and then work from there. And finally, a microservices-based architecture, if done right, can be very resilient because whenever one piece fails in this whole picture, it doesn't necessarily have to take away the whole system down. Every failure is confined to individual microservices. And if you look at the development lifecycle, microservices are developed individually and they're deployed individually. So you have individual microservices, each with their own developers, their own deliverable, their own build test and release lifecycle. And this makes deployment a lot easier for teams because everybody can deploy their own microservice without asking anybody else. So there's a lot more decoupling going on, a lot more independence going on, and that makes it easier to deploy many, many times, even many times per day. So my customers, when they learn about microservices, they tend to ask questions like, how do I migrate my existing application, which is monolithic, into a set of microservices? How does networking work? What does it mean for my network if I now have lots of services talking to each other? How should I go about implementing service discovery? How do these microservices talk to each other? How do they know who to talk to each other? And what about deployment? How can I manage many, many, many individual deployment pipelines? And what services should I choose from all of the AWS portfolio to implement my microservices and how? So this is where Patrick and Julian are coming in. And I'm very happy to introduce you to Patrick and Julian here. They're going to share some of the lessons they learned as they did exactly that kind of migration. So Patrick.
Thank you.
Thank you.
So I'm glad you're here today. and I would like to take you on to our journey from migrating our monolithic backend to microservices and subsequently leveraging a couple of AWS services. I would like to start with a common use case that we have. Can you imagine how many possibilities you have to configure your dream car? For example, here for the new BMW 3 Series that has been launched a couple of weeks ago, you have the possibilities to choose from 7 engines, 12 colors, 14 wheels, 11 upholsteries, 7 trims, and additional 90 optional equipment. There's a lot to choose from. And from a front-end perspective, you need, on the one hand, all the vehicle data to show it to your customers, and on the other hand, you need also functionalities to check if your dream configuration is really constructible. Within the BMW group, there existed a huge demand on getting these data, vehicle data, and also functionalities, like I said, the constructability check, from a central platform, so that not everyone needs to take care about where to get the data and to rebuild commonly used functionalities. Therefore, we created the unified configurator platform. And the configurator platform is currently used by about 13 application and web front ends. For example, as you can see, from various car configurators like native iOS applications, or from front ends. But the platform is also used from applications that have an AI purpose or for creating an offer for our customers. So let us now have a look at our platform for a more or less high-level perspective. Our platform exposes RESTful APIs and expose all the necessary product data and functionalities like the constructability check, or price calculation services, or a virtual garage to store the configuration that you have configured. To expose all the data, it is necessary for us to import these data on a frequent basis from the BMW landscape. And our platform is currently actually serving about 100 million of API calls per month, and we are supporting all BMW Group's markets and brands. So after you have now heard about what our platform is doing, I would like to take you on to the journey on how we came with a monolith to microservices and subsequently to AWS. Everyone is talking today about microservices, but from our perspective, it is worthwhile also to think about monolithic systems, because for us, the monolithic system provided a fast development at an early stage and to have a production-ready MVP. We do not have to handle all the challenges that come along with microservices, like data synchronization, or how you are doing logging, and how you are doing debugging with microservices, and so on. Nevertheless, as our monolith growth, we had some challenges that we were faced with. Small changes led to a rebuild of the complete application, and implementing new requirements led to a lot of refactoring. So in a nutshell, we had a lot of complexity to handle with, and the monolith became too complex, and the development became slow. So therefore, we had to rethink about it and go into the next step to microservices. So at the same time as we broke up our monolithic system into microservices, we also introduced the concept of the API first approach. The API first approach gives us the opportunity to specify the API up front and to have the chance to see the actual implementation before they start. Also having the microservices now and the platform became more and more complex, we had to think about going the next step. So in a nutshell, the microservices helped us, but we had to think to get the next step. For example, we had questions like, how can we provide our platform on a global basis with low latencies, or how can we get a broader solution scope to satisfy new business requirements? Let us now see how we did the transition. We followed an approach like lift, sync, and shift, and on-premise we had different artifacts. We had the API specification and the authentication informations from the API. These one we had to transfer it into the API gateway. Next, our microservices are all based on Java applications, so we have a GlassFish 4 application server. These one we have Dockerized and deployed to Elastic Beanstalk. On-premise, we had a couple of Oracle databases. For cost efficiency purposes, we changed here from Oracle to Postgres and are using the RDS, Amazon RDS services. As I told before, we need to import a lot of data into our platform to expose these data to our customers. Therefore, we have import jobs. The import jobs were written as PL/SQL statements on-premise. These we have rewritten as Java code and deployed to ECS and AWS Batch as a queuing system. So let us now move on to have a more precise look at our architecture. So whenever a customer is calling our APIs, he's using a public domain. This public domain is registered within the AWS Route 53. And in front of the API gateway, we are using AWS CloudFront. AWS CloudFront is for us an important element in our global distribution strategy, as it provides us, on the one hand, the caching purposes for caching frequent requests, and on the other hand, we do have a fast entry point or an entry point near to our customers into the AWS backbone. And the API gateway is generated out of Swagger, and for all requests that is entering into our solution, we do use a combination of AWS DynamoDB and AWS Lambda. Within the AWS DynamoDB, we are storing API keys, and together with the rights, which API key can retrieve which API that we have. Lambda, in this context, is doing the complete authentication purposes for us. As soon as a request got authenticated, we are using a VPC link to have an entry point into our VPC. The VPC consists of 3 different subnets. In one subnet, we have all our load balancers. In another subnet, we have our applications. And in the third one, the databases. As the VPC link currently only works with network load balancers, we had to find a solution on how we can address our different microservices on a path-based way. Here we came up that we can reuse the Nginx that comes along with Elastic Beanstalk, and Nginx has the job here to forward the request to the subsequently microservices. To identify our microservices, we are using Route 53 again with a private hosted zone. Within this private hosted zone, each microservice, as soon as the environment of the microservices is created or set it up, registers an entry within this private hosted zone. And so we have the possibility to address the endpoints of our microservices. So let us now move on to the environment of a microservice, how the tech stack looks like. We are using Elastic Beanstalk as it provides for us the right abstraction on focusing on our core mission to provide new services to the platform. On Elastic Beanstalk, we are deploying Docker containers with our Java application, and we are using security groups and knuckles to restrict the traffic to our application. Each microservice of us has an own persistence layer. The persistence layer is, in this context, a database within the Amazon RDS services where we get a Postgres instance on a multi-AZ setting. Now I would like to hand over to Julian, who will give you more a deep dive onto our architecture.
As we now have an overview about our architecture, I want to go into 5 different fields of our solution to show you some details. As first, I want to show you how we do service discovery and continuously improve technical decisions. You already know this big picture from Patrick. Within our VPC, we have a private hosted zone. Each microservice should be accessible via an internal domain name. For example, microservice A.bmw, microservice B.bmw, and so on. The microservice itself registers his application load balancer within a root 53 record. And if the microservice later changes, the microservice takes care about his own reference within root 53. We use this as an internal service discovery, and now each microservice can talk to each other. And also the proxy, which Patrick introduced earlier, routes the traffic through the internal domain name to the corresponding microservice. If we release new software, we use mostly the deployment strategies within AWS Beanstalk. For example, you can use their rolling updates or immutable updates. Beanstalk takes care about the whole deployment cycle. For example, checks the availability of new containers or instances and cuts over the traffic if the health check pass. If we change more, for example, the heap size configuration or pool size configuration in combination with a different EC2 type, we have a more risky change. Even after a full regression test and a load test, something can go wrong on production workload. Even after, yes, we can use root 53 rated routing to handle this risk. We deploy the same microservice a second time, for example, with a different configuration, different EC2 types. In root 53, it's possible to create multiple records for the same domain name and route the traffic to multiple targets. Here in this example, 99 to 1%. This enables us to verify our new tech setup with a predefined amount of traffic. If everything goes well, we cut over to the new microservice and delete the old stack. All this can be used to change whole tech stacks, not only to check some minor configuration changes. For example, here, we deploy the same microservice A a second time and use the rated routing as before. The second microservice can run, for example, in AWS Lambda with a private API gateway and store the data in DynamoDB. At the end, we provide the same REST API for our client systems, just with another tech stack. If everything goes well, we cut over to the new microservice and delete the old stack. In the fast-moving tech world, for us, it's important to build architectures which are easy to change. And root 53 gives us here a lot of flexibility. The second deep dive topic has a similar intent. How do we deploy Lambda functions? We use Lambda functions in different places of our architecture. For example, to verify the API keys or to stream data out of CloudWatch. In some cases, the functions are crucial for our overall availability. We store all relevant artifacts for our Lambda function within our on-prem Git repository. The Jenkins takes the artifacts and uploads them. The code goes to S3, and the CloudFormation stack is initially created or later updated. Code deploy deploys the code from S3 to the new created Lambda function. But how do we deploy now a new version of our Lambda code? Of course, we create a new version and an alias. An alias is like a pointer to a version. Then we can set a deployment preference within code deploy. For example, shift the traffic linear within 10 minutes to the new alias. If CloudWatch detects errors, code deploy will roll back to the old version. If not, the new Lambda code is running. The third deep dive topic is important for our microservice architecture. We try to make every microservice independent as possible. Our platform supports around 140 countries worldwide for all BMW Group brands, and this requires an adequate data management. As Patrick mentioned before, we get the raw data from the BMW landscape. We have different microservices which need the data from the on-prem data sources. For example, here, microservice A, B, and D. We also have microservices which aggregate the results of other microservices. Here, microservice C. A, B, and D can import the data almost independent, but microservice C has to wait for A and B. In a perfect world, each microservice is independent, but in reality, even if you're on a green field, it's not always feasible. For us, it was important that we cut our microservice in a way that we can accept eventual consistency. Also, we don't want distributed transactions. The data processing has to be done on different time zones, like you see in the upper right corner, for example, Central Europe in orange or North America in blue. In the lower right side, you see the batch jobs from the microservice A, B, C, and D within a day timeline. We need the right job executed for the right market at the right time. All that has to be optimized as possible to reduce the time for eventual consistency. Also, that has to be resilient and, of course, cost efficient. For us, ECS and AWS Batch was the right solution here. We want to bring the data from the on-prem data sources via ECS to our microservice. To execute the right job at the right time, we use AWS CloudWatch events and AWS Lambda as a scheduler. Lambda creates up to hundreds of jobs in AWS Batch. AWS Batch works as a queue for the ECS tasks. We have also different queue priorities based on the business criticality of the data. Dependencies the dependencies you have seen before are handled through the depends on property within AWS Batch. Our ECS clusters use spot instances to reduce the costs. In addition, we use this setup not only for the data imports, we also use it for some offline data processing, which runs in a Docker container. The next deep dive topic shows a similar intent. So how do we leverage Lambda for a special use case? We have to check ad hoc hundreds of vehicles against their constructability rules. Due to the product data updates, it's not possible to pre-calculate the vehicles. Also, the time when we have to provide this calculation or the constructability check is not known. So this use case is really hard to master on-prem or without serverless technologies. We found a good solution with AWS Lambda. We spread the vehicle data, including the constructability rules, via an orchestration functor to a bunch of Lambda functions. Each function checks the constructability of one vehicle at the same time, and the orchestration Lambda consolidates all results. If all checks are done, the overall result is returned. Some hundred of constructability checks takes overall just 1 or 2 seconds. This solution is good for our special use case, but you have still to consider some constraints. For example, we restricted the parallel execution to a maximum of 50 Lambda functions. Also, we know that this service is not called more than some 100 times a day. If you will run more and continuously workload on that architecture, you should consider a more or less predefined compute cluster. The last deep dive topic is about our environment staging. Our dev teams deploy every year hundreds of features, and the features need to be tested and integrated. You already know that our infrastructure is defined in CloudFormation as infrastructure as code. And our dev teams follow the Git flow workflow. So why don't create for every feature branch a distinct and isolated tech stack? We have done it. And the dev teams can start a full demand environment within minutes. Jenkins pulls all CloudFormation templates out of the Git repository and creates the microservice stack. The microservice stack contains everything you have seen before in this presentation. And if the stack is up, the Jenkins deploys the feature branch to the microservice. Then the team can run the CI pipeline, do manual testing, or do whatever they need. In general, we use the most cost-efficient EC2 types for this, and also we take care that the dev teams don't let run this on-demand environment longer than necessary. After a certain time or a master merge, the on-demand environment should be terminated. Overall, our high infrastructure automation enables us to provide our dev teams this environment on demand. Now we talked a lot about our architecture, but before I come to a conclusion, I want to talk about a nice event, our first own game day. The goal of the game day was to train our operation team. They should be well prepared for the potential production problems. During the game day, the teams have to solve production problems on the real architecture. For this, we installed for every dev team an own AWS account with all stacks you have seen before. And, of course, it's a game day, we use gamification as an incentive. Each team gets points for the overall availability of their system. The points were available on global leaderboards, and this really sparked the competition. Then a Chaos Monkey team brought fun into the situation, and the dev teams had to clean up the chaos of the monkeys as fast as possible. For sustainable improvements, each team could earn additional points. The additional points were to improve the DevOps cycle, to support the DevOps cycle. The feedback was really great. The game day showed that it's a great opportunity to deepen the transferred knowledge in a fun way and to gain hands-on experience through simulated incidents and for the operation work. We decided to do such a game day more often, and by the way, it's really a lot of fun for everyone. Let's talk about what we have learned during the transition to AWS. We made our microservice cloud-ready with the refactoring to a microservice architecture. Here it's really important to make the microservice independent as possible, on runtime and on development level. Don't try to make it too perfect. It's good if you have an initial solution and optimize it later on if it's necessary. Stop talking, start building. All love to discuss technical solutions, but sometimes it's better to try out a solution with a short feedback loop. The speed that AWS provides is really fast, and you have to keep up here. For us, it was good to have initial trainings and also certifications. A good start is also to subscribe to newsletters or read interesting blog posts. Everyone in the team should gain regularly hands-on experience on new or unknown services. A common understanding is that the cloud is almost infinitely scalable, but be aware of AWS soft and hard limits. Doing the transition 100% in-house was for us a game changer. With a self-organized BMW team, we could focus on the lift, think, and shift to AWS instead of managing the overhead which external service providers have. Last but not least, for us it was perfect to have someone on our side to discuss initial technical solutions. AWS professional services, what was good for us to accelerate at the beginning instead of starting at point zero. And thank you, and now it's your turn.
Thank you, Julian. So now it's your turn, actually. Hopefully you now are motivated to build your own microservices or even to split up your existing monolithic applications and create a set of microservices. So to that end, it's useful to check out some best practices that we learned from Patrick and Julian and that also are established in many other microservices projects. Now, we're all techies, right? We like to get deep down and start building services. But before you start building something, it's useful to start with a design phase without the technology part and really think about how do you want to structure those microservices. And there's a lot of customers that ask me, okay, how should I cut my microservices? So check out domain-driven design techniques to help you identify the boundaries of each microservice. And there's a whole class of literature around domain-driven design. This is an example book you can use as a starting point if you haven't dived deep into domain-driven design. And it helps you focus on the core domain of each service. So what is a domain here? If you're looking from a business point of view, whenever you change the language of the business side, this is a good indicator that you're changing the domain and where you want to split up in different service. So for instance, customers are one domain, the car configuration properties are a different domain, the sales cycle is another domain. So you can start from the business side up and cut your services based on business domains here. It helps you put the domain model at the center, which is really the driver for your application, not the technology. It should be really the business domain here. And it also helps you collaborate between your business people and your technology people, be it developers or operations people here. The other thing is when you look at microservices, there are a couple of principles that have been established over time. So microservices are always decentralized, which helps with the whole detaching with the whole independence thing. Microservices tend to be independently developed, which means that you may want to put microservices into the hands of different development teams and each of them owning their microservice as their own product, if you will. Microservices should behave like a black box, so you shouldn't be able to look inside the microservice and try to game the system or try to use this to I don't know, optimize something. Every microservice should really be behind its own API, so that gives you the freedom to change and optimize the microservice without having to ask anybody else for permission. And then microservices can be polyglot. So this is a great driver of freedom for developers because each microservice is developed independently. You can choose a different technology stack per microservice depending on what you want to solve here. So it's perfectly okay to have a different type of database for each microservice, to have a different language for each microservice, and to choose a completely different technology stack per microservice, as long as it helps you create better services or simplify things or be more productive. And also, you should focus on each microservice doing one thing really well. And if you catch yourself implementing more and more features into the same service, maybe this is an indicator to split up the work into multiple services so that each service can be implemented independently from each other, and then you can realize the benefits of having individual microservices. And finally, when you build your microservice, you also got to run it. You build it, you run it culture that comes with DevOps applies really well to the world of microservices. So it's worth taking a look into DevOps a lot more. So in order to understand this, here's a book that helped me a lot, learn a lot about microservices. This is one of the most important books about building microservices. And it covers a lot of the things from a technology point of view, but also from a cultural point of view. How does the development cycle work? How does deployment work? What should you keep in mind in terms of security? So this is a really good start into having a better full picture on how to develop these things. And finally, we touched upon DevOps. I've been to so many meetings that had the topic of DevOps, and then people started talking about Jenkins and tools and technology. And this is not DevOps. DevOps is really a methodology for how you want to bring developers and operations and how you want to bring those people together to run your microservice together, right? So when you think about DevOps, remind yourself that DevOps is about systems thinking. It's about everybody taking a look at the bigger picture and making sure that you're not falling into the trap of silos, and instead, everybody in the team should look at the whole picture, even across different departments of your company. So this is about systems thinking. It's about understanding the system as a whole. DevOps is also about amplifying feedback loops. Once you connect the developers with the ops people, you can then start monitoring everything, and then you can feed back the monitoring data back to the developers so that they know how to fix things directly from what your customers or from what the consumers of your microservice are seeing. And finally, DevOps is really a way of installing a culture of continual experimentation and continual learning. And we've seen a couple of examples here, even with the game day approach that BMW took here. So if you want to learn more, there's a great blog post by one of the founding figureheads of the DevOps movement. If you haven't done before, I really recommend reading the Phoenix Project. This is not a textbook. This is really a novel. You can actually read this at bedtime. It's a story about an IT department and its IT manager who suddenly needs to cope with a lot of change, with a lot of chaos, and starts implementing a lot of the best practices from manufacturing actually in their IT department. And I think having a manufacturing company like BMW and then using the manufacturing know-how of lean production and looking at the bottleneck in your production line and applying those principles to your IT, this is a really nice story here. And then there is a handbook coming out of that really puts these lessons into practice for you. So let's take a look at how to implement microservices on the AWS side. And there are a couple of patterns that we saw at BMW that you can reuse for your own microservices. And one pattern is how to create a very simple microservice with just AWS Lambda. So you can use Amazon S3 to host static data like HTML and JavaScript and fonts, and use Amazon CloudFront on top of that to create a very simple user interface layer, which is basically static HTML5 that serves as the client in the web browser. And then you can create your microservice just with API Gateway and AWS Lambda. So API Gateway gives you the API layer that helps hide your microservice as a black box. And then Lambda is where the business code is running. And this is a very simple way to deploy your business logic in a simple Lambda function. And finally, you can use any database. In this example, we're using Amazon DynamoDB, which is a very easy-to-use database. No need to manage anything. You simply set up your table and start filling those tables with data. And there is your microservices architecture in just 3 easy steps. Of course, if you like containers, you can do the same. You can use the same front-end approach with Amazon S3 and CloudFront. And then you would need API Gateway again, but this time you would put your containers inside a container environment such as AWS Fargate in this example, or ECS or EKS. And you could use an application load balancer to manage the load from API Gateway and distribute it into your container fleet. And again, you can use any database you want, or maybe you want to use multiple databases depending on the kind of data that you're running. It could be DynamoDB, or it could be Amazon RDS, or it could be Elasticache for caching. So when you have multiple microservices, they probably want to talk to each other. And that introduces us to the wonderful world of messaging. And instead of fretting about how to use old school enterprise service buses and other heavyweight messaging technologies, you can go really lightweight by using things like Amazon SNS. So simple notification service is a really easy to use messaging service on AWS. You can publish messages on SNS from a provider microservice, and then the message gets written into an SNS topic, and you can structure the message flow using SNS topics, And if you want to persist messages for some time until they are processed, you can use Amazon SQS, which is Simple Queue Service, which helps you buffer those messages until they are fully processed. And then your consumer microservice can simply pull messages from an SQS queue, process them, and there is your new super lightweight enterprise service bus, which is not, which doesn't introduce any administrative overhead, and it's very easy to set up. And finally, we also learned about how to do service discovery using Route 53, and this pattern is really worth studying because it makes it really easy to do service discovery without having to run a full service discovery suite of products. So in this case, we're using Amazon Route 53, and you can use Route 53 DNS records to do the mapping between your service name and the IP address where that service is available. And if you set up your fleet of microservices, in this case, we're using containers as an example, you can set up Amazon CloudWatch to monitor the lifecycle of individual containers running on your container fleet. And you can use AWS Lambda as a dynamic way of updating Route 53 records. So this is how it works. If you start a new microservice in your container fleet, Amazon CloudWatch will automatically detect the new container running. It will notify AWS Lambda, and then you can use a simple piece of code inside Lambda to update the record in Route 53 so that the new entry shows up in Route 53 and other applications can start using this new instance that you put into your fleet. And similarly, if something goes wrong or if you decommission an instance of a microservice, then the same mechanism goes into effect. So CloudWatch will detect that the microservice has been shut down, or maybe it has malfunctioned. It will call the same Lambda function. The Lambda function will update the record in Route 53, and you get a very near real-time representation of the state of each service in Route 53 so that other services can check, okay, this one is not showing up anymore. Where's the next node I can talk to reach this microservice here? Very easy to use pattern, very powerful because it's very resilient, and you don't have to administer anything. It is completely self-administering. So let's summarize what we covered today. First, everybody talks about microservices, and yes, they are cool, but monoliths aren't really bad. In the beginning, it's okay to write a monolith so that you get the first minimum viable product up and running, and you start validating your approach and start getting your project running. After that, moving to microservices can have a lot of advantages. It can introduce a lot more agility as the service becomes more and more complex and grows. And this means that you should become a builder. And many of my customers from the manufacturing and automotive space, they are used to decades of outsourcing everything to vendors. And this is a very slow way of developing stuff. And it also doesn't give you a lot of control because you need to go through a lot of conf calls, meetings, until you get anything done. Instead, become a builder yourself. It has never been easier to build something as today in the cloud because you can do everything with API calls. So learn how to build, learn how to experiment. Don't fret over creating the perfect solution from the beginning. Start with something that works and work from there. There's lots of best practices available. Don't forget about domain-driven design before you start writing code. Try to learn some microservices patterns and think about DevOps as a way of life instead of just a set of tools. There's a lot of services on AWS that can help you build microservices without having to think about administration and setup, which keeps your head free for really innovating on top of your use case and leaving all of the hard work to those services. So check out things like Lambda, Route 53, API Gateway, ECS, and all these other services. And if you need some help, feel free to work with AWS professional services or partners or AWS support, and they will help you set up everything and help you transition into this new mode of operation. So with that, thank you very much for coming, and enjoy the rest of reInvent. Thank you.